Welcome to the public AI for You Cafe on October 13th. The speaker today is Manolis Kobarakis. Welcome, Manolis. Hello. And my co-moderator, Teresa. Hello, Teresa.
Hi.
Hi. And I'm Carl McWilliams from Grassroots Arts. Manolis will today talk about semantic technologies for Earth observation. Manolis is professor and director of graduate studies in the Department of Informatics and Telecommunications, National and Kapodistrian University of Athens, and an Euro AI fellow. So first, before we start, please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers express their personal view and opinions. This is not necessarily the official AI for You project opinion. So what's the cafe about? It's an online forum to gain insight into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. So also I want to welcome you, visitors of the cafe. Great to have you here. I know it's a busy time in the moment for the AI ecosystem. And please write your questions to the speaker in the chat on the right side, and I will read them afterwards to the speaker. And now I want to officially introduce our speaker today. Manolis Kobarakis is a professor and director of graduate studies in the Department of Informatics and Telecommunications, National and Kapodistrian University of Athens. He leads the artificial intelligence team. He's also an adjunct researcher at the Institute of the Management of Information System, IMIS, of the Athena Research and Innovation Center. He holds a PhD in computer science from the National Technical University of Athens and a Master of Science in Computer Science from the University of Toronto and a Diploma Bachelor of Science in Mathematics from the University of Crete. He's a fellow of the Euro AI. This is the European Association for Artificial Intelligence since 2015 and president of the Hellenic Association for Artificial Intelligence. Manolis is currently the coordinator of the project Extreme Earth, which develops deep learning and big data techniques for satellite data from the Copernicus program. He also participates in the projects AI for You and AI for Copernicus as technical manager of this project, which brings Copernicus data to the AI for You platform, and DeepCube, where he leads the work on semantic data cubes. This is very impressive. So welcome, Manolis, to our cafe today. And now I give you the floor, and then you can say hello to everybody and show your presentation. I will make you now the moderator. One moment, Manolis. Now you're the moderator, and you may open your presentation, and we are looking forward.
Thank you, Teresa. Thank you very much for the kind introduction. So hello to everybody. Thank you for being here for this AI for EU Cafe. So as Teresa said, I'm Manolis Kobarakis. I'm a professor at the University of Athens and a participant in the Sextant AI for EU project, which is not about Earth observation. It's about AI. It has some emphasis on Earth observation. I'll tell you about this in the last slide of my presentation. So essentially what I will be presenting you today is work that has been done in other funded European projects and are about the use of AI and especially semantic technologies, an area of AI in which Europe is very strong, to satellite data, to Earth observation. So why are we interested in this area? it's because now there is lots of Earth observation data around. This availability of free and open Earth observation data started originally in the United States with the Landsat program. And now Europe has essentially leveled up the field, or even exceeded the lead of the US in this area with its Copernicus program. And Copernicus makes available lots of interesting Earth observation data. And it has a very big economic impact. So from this Copernicus market report of 2019, we can see that the overall investment in the program has been so far close to 8 billion. And the cumulated economic value that we can estimate that this investment has generated is 16 to 21 billion. And we expect a lot more value to be generated with the program as it continues in the future. Now, if we turn to the technical issues and we consider Copernicus data, the data produced by the program Copernicus, we can see that it's a paradigmatic case of big data. So we have a very big volume of data. So you can see, for example, from this table that we are talking about petabytes of data. So in 2019, the total amount of data that was produced by the 4 satellites that were in orbit, rather the 4 satellite missions that were I have here, Sentinel-1, Sentinel-2, Sentinel-3, and Sentinel-5P are 7.5 petabytes. So we have volume, we have velocity. So the rate of production of this data is very big. We are talking about terabytes of data in this case. And very importantly for us and the work that we have done is variety. So the Sentinel satellites of the Copernicus program consist of different type of sensors. For example, S1 is a radar satellite, S2 is a multispectral satellite, and the processing of these data that is produced from the satellite is different, and we get different kinds of products starting from the raw data. And typically the data sets that are produced from Copernicus, they are not used just by themselves in an application. Typically they are together with other kinds of data like aerial imagery, in situ data, or other collateral information like media data, public government data, etc. And finally, this wealth of data is basically processed by various actors, and information and knowledge is extracted from this data. And this information and knowledge is also big, and similar big data challenges apply. So if we can see, for example, I'm sorry, I'm trying to find my slides now because I lost them for a minute, but now I found them. Apologies. So if we process this data, and we process, let's say, 1 petabyte of Sentinel data. With the back of the envelope calculation, we can see that we have something like half a petabyte of classes of objects detected in this data. So even the information and knowledge that is extracted from the Copernicus data is big, and we have to take appropriate care of that.
Manolis, I have to
yes.
interrupt. The PowerPoint is not to be seen by us anymore. Can we try this again? Try to call it up. Just, I think you're still the moderator. One moment. Yes, you are the moderator. So screen sharing. Yes, perfect. Perfect. Thank you. Sorry for interruption.
Sorry, I was distracted by the chat, and then everything.
Yes,
Can
perfect.
you see my?
Perfect.
But I don't see it now myself. Sorry.
Still see it? I see now high-level objective of our work.
Can you see it now?
No.
Maybe you undo me as a moderator and do me as a moderator again, yes. And we do it again.
Yes, one moment. I make myself a moderator. I even share my screen. What is the AI for you web cafe? So, and now I make you again the moderator. Yes. Yes, I see it. I see your screen.
Okay, I can see it too now. And now in full screen, can you see it, yes. Please?
Very good.
Okay.
Very good.
Excellent. So apologies for these problems to everybody. So the high-level objective of our work in this context since 2010 has been to bring computer science and Earth observation together to solve interesting problems of commercial, environmental, or societal value. And we had a lot of funding from the European Commission to achieve this. And so this was a high-level kind of objective. And if we look at the technical details, then essentially what I think my group has contributed for the last 10 years in this area is we demonstrated how useful it is to take this big data that is currently hidden in silos and to make it available on the web as linked data by publishing their data, metadata, information, and knowledge extracted from this data using semantic web and linked data technologies like schema.org, RDF, Sparkle, OWL2, etc. And in that way, be able to develop interesting and valuable applications. And we have chosen linked data as our technology because it fits this paradigm very nicely. It can help us unlock open data that are dormant in their silos. We can make the data available on the web so they can be easily found by other interested users. And very importantly, we can interlink the data with other data. For example, data from the European Union Open Data Portal. So if you go, for example, to our website, to the website of my team, you can find Earth observation datasets like the Greenland cover or the Urban Atlas datasets being made available as linked data. And you can think about interesting linkages to other datasets. So you can link, for example, Corinne Lancaver with administrative area datasets from a certain country, or the global administrative area datasets, GADM, that we have linked Corinne Lancaver with. And in that way, for example, be able to see for a certain area, okay, a certain administrative area, let's say the area of Athens, for example, what is the land cover of that area, and you have this interrelated information. Or you can relate Corinne Lancaver to information that is on OpenStreetMap and so on. So you can get a lot of value from these linkages, and you can develop interesting applications. What we have learned from the work that we have done with applying linked data principles to Earth observation data, we learned that in that way we can make Copernicus data more easily discoverable by search engines and new services like Google Dataset Search by using technologies like schema.org for encoding the metadata of these datasets. Once the datasets are transformed into linked data, like the Corinne Lancaver dataset, we can also get the nice interlinking that I just described. And in this way, we can talk about having geospatial knowledge graphs, and we have such a knowledge graph called Yago2Geo that you can check out. It's an extension of the knowledge graph Yago2 with geospatial information. You can enable the querying of this data using Sparkle, or even using natural language. I will talk about both cases in a minute. And you can also visualize these graphs in an interesting way. And in general, what we have seen is that it becomes much easier for software developers who may not be specialists in Earth observation to develop their applications. Of course, they have to know semantic technologies, but I suppose this is something that can be easily mastered. Now, over these 10 years, what we have worked is we have worked on a pipeline for what we call big linked Earth observation data. And the pipeline basically starts from the satellite when the data becomes available. The data comes to the ground segment of the satellite where it is ingested. It is processed, and products at various levels are produced. These products are cataloged and archived, and then somebody can come in and ask for such products, okay? Once this person discovers the products that he or she needs, then he can run some sort of machine learning algorithms to extract knowledge from this product. Then what we do is this knowledge, we transform it into RDF, we interlink it with other data, we publish it on the web, we store it in appropriate stores, appropriate DBMSs, where we can pose queries or ask questions in natural language and get answers. And we can, of course, search, browse, explore, and visualize this kind of data to develop applications. So let me start by looking at some stages of this pipeline and tell you what work we have done or are doing now in this area. So I start with dataset discovery. In this area, what interests us very much is to be able to discover datasets by posing natural language queries. So to say, for example, to a question answering engine for datasets, find me sentinel images that can be used to detect burned down villages in the Rakhine state of Myanmar during August and September 2017. We actually did such an application with the European Union Satellite Center, and these people are interested in posing such questions to an appropriate search engine because they want to find appropriate information of that sort for the kinds of reports that they are building for the European Union whenever let's say a humanitarian crisis is taking place somewhere on Earth. So how do we answer such a question now with the question answering engine that we are developing? This is work done in the AI for Copernicus project that Teresa mentioned earlier, and it also benefits from, sorry, I meant to say Carmen, that Carmen mentioned earlier, and it benefits also from work that we are doing in a national Greek project called GeoQA. Okay, so this question can be answered by finding the geographic area of the Rakhine state of Myanmar from knowledge graph Yago to Geo. Find what kind of sentinel images can be used to detect bird areas using a knowledge graph that we have developed, which we call the Copernicus knowledge graph. And the answer in our case, in our question, is Sentinel-2. And then find Sentinel-2 images that have been taken in August or September 2017, and their coverage intersects the geographical area that we just found using Yago to Geo. And for that, we use image metadata, of course. So this is the process, and as you see, this is something very complex, and the development of such a question answering engine is indeed a challenge, and this is something that we are doing at the moment in AI for Copernicus. Essentially what I'm doing here is I'm visiting these stages one by one. So I'm not telling you anything about this interesting knowledge discovery step. I mean, this is an area also where AI techniques are making a lot of interesting contributions, especially the use of machine learning to extract knowledge from the satellite images. But I'm not an expert in this area. I'm an expert in semantic technologies. So this is why I'm continuing with the rest of the pipeline. So as I told you, once we have discovered this knowledge, let's say we have a satellite image, and from it we can discover, for example, the types of crops that are in a certain geographical area. Then this knowledge will transform into RDF. So typically this knowledge will come out, will be produced in a shapefile, yeah? And we transform this shapefile into RDF. In fact, we have a tool which we call GeoTriples that can take as input many formats, many, let's say, traditional formats of geospatial data, like shapefiles, for example, or GeoJSON, and transform them into RDF, okay? This happens in two steps. In the first step, some mappings in R2RML and RML are produced, and then a mapping processor executes basically these mapping and these mappings and produces the triples. And we have very recently developed in project Extreme Earth an extension of GeoTriple Spark, a new version rather, that runs on Apache Spark, and we have shown that it's very scalable, and it's really the best system for doing this kind of work right now. Continuing with interlinking, we have a system called Jedi Spatial, where the idea is that we have data sources that are geospatial, and we would like to interlink them. So, for example, we would like to know which area represented in an administrative areas data sets of a certain country has a certain land cover, and we want to build this link. We can use the spatial, and again in our work we have shown that it is this a very efficient system, very scalable, and it beats all the relevant competitors. Continuing with the storage and querying and question answering, I talked about the question answering already. In the area of querying, we have a system that we call Strabon that we have been using for a number of years. It's built on top of PostGIS, although it communicates with other databases like MonetDB, for example. And it's a query engine where you can store linked geospatial data and write queries either in GeoSparkle, which is a Node.js standard, or in ST-Sparkle, which is a language similar to GeoSparkle, but it also has a temporal component that we have developed in Athens. And we have papers where we show that Strabon is scalable and efficient. And we are currently working on a more scalable and efficient version of Strabon called Strabo 2, where we utilize Apache technologies and things like this, and this is what we are doing in Extreme Earth. Another very useful system that we have developed in the past is on top spatial. The reason that we developed this system was the following. I mean, it's okay for us as researchers and people that are interested in linked data to actually say that somebody who has a shapefile should transform it into linked data and then use our beautiful technologies to develop his or her application. The reality can be more complex than that, and sometimes it is more complex than that. So in reality, you might have people with geospatial data that do not want to transform their data into linked data, but still they would like to benefit from semantic technologies. So we have a solution for these people as well. These people can leave their data in their sources, be them shape files or available through certain OGC APIs, or in geospatial DBMSs like Oracle Spatial, for example, or PostGIS. Okay, so the data can stay there, but the users can benefit from semantic technologies by having an ontology of the domain written in OWL and being able to write a query in GeoSparkle, okay? And this query, with the help of mappings from ontology terms to the schemas of the data sources, is eventually transformed into SQL. It runs on the, let's say, geospatial DBMSs or on virtual tables that we built from the shape files, for example, and in that way the answers are computed and returned to the user. Okay, so basically we offer all the choices to the users that would like to work with semantic technologies in Earth observation. And in most recent work we apply these ideas to data cubes. So we are assuming that the data is stored in a data cube, but we are addressing the data using ontologies and GeoSparkle, and we are using on top spatial to basically implement what we call a semantic data cube. And this is work that we do in the DeepCube project that also studies explainable deep learning pipelines for Earth observation data. Finally, we have a very nice system called Sextant for the development, for the production of layered maps. So we can have the data as linked data stored, let's say, in Strabon or other RDF stores or in on top spatial. And Sextant, what it does is it allows us to create maps like the one that I'm showing you, by essentially allowing us to pose queries to the various databases and visualize the results. So for us, Sextant is something like the GIS tool for linked geospatial data, the GIS environment, the QGIS, let's say for linked geospatial data. And here you can see a map that we have built for the food security use case that we have in Project Extreme Earth, which I'm coordinating. And here you see, or you were supposed to see, because it's a PDF and now it doesn't have the animation. I apologize for this. Ideally, here you would see ice basically changing its dimensions over time as time goes by. So we in Sextant you can also build temporal maps. And this is a very interesting feature, and we do this work in the polar use case of Extreme Earth, where ice mapping in the Arctic region is the main problem that we study. And finally, just one word for the our work in AI for EU. The technologies that I presented to you, or rather some of them, are used in one of the pilots of AI for EU, the agriculture pilot, where the idea is that we have vineyards. So actually we have a pilot that takes place in vineyards in Spain. And one of the goals of the pilot is to determine the quality of the various grapes produced. And in the pilot, we used various technologies like computer vision technologies for taking pictures in the vineyard. Our semantic technologies are used in developing the knowledge graph, where the information from the from the fields, the information from models of plant growth, the information from the cameras is stored, and so that it can be made available to develop the pilot. So this is an interesting dimension. This is our contribution, in fact, to AI for EU. Thank you very much. This is where my my presentation finishes. There is lots of interesting projects that have funded our work over the years. So I'm grateful to the funding agencies, European and Greek, for these funds. This you can find my web page easily by googling my name, and if you need more about my work, you will find it there. And I'm happy now to take any questions that there might have.
Yes, thank you, Manolis. Thank you very much for this really interesting presentation. And as you always know, if you have more questions later, also send it to Manolis directly. But in the moment I start, as My question is, like for me, all this what you're doing is super interesting because this example you can really make precise questions. The example you gave about, for example, humanitarian crisis, which villages were burned down in 2017, which is super interesting. And of course, that comes to my question: do you think your semantic technologies and an eye could help to solve critical and more complex societal challenges such as climate change and prevent hunger? And if yes, how?
Well, that's a very difficult question. Well, I suppose that the contribution of semantic technologies comes after the use of other technologies. So I think first of all, for climate change, for example, very soon we will have data from the digital twins of the Destination Earth initiative of the European Commission. So this will be very, very rich kinds of data that will allow us to tackle climate change. So essentially, I think what we need there, and we will see there, a pipeline like the one that we have worked with, where you are using mostly machine learning algorithms to extract interesting things from this raw data that the digital twins will provide rather. And then I think we will be using knowledge graphs and semantic technologies to represent this knowledge and to make it available to enable decision making. So I don't think the semantic technologies will be very useful at the lower level. There are other technologies that will be very useful there, like machine learning. But at the higher level, they will be very useful. And talking about machine learning as well, I mean, there is now a very interesting question which is related whether semantic technologies can be put together with machine learning technologies, and in that way we come up with technologies that are more explainable, for example, that are more responsible and so on. So the answer is yes.
Yes.
Semantic technologies can contribute to that.
That was a difficult question, I know. So, and a great answer. And now, Teresa, do you have a question?
Yeah, I have a question which is more a technical one. I'm not quite sure how exactly you would connect data. For me, normally I go on Google and click on documents, and then they are connected documents, but not the information or the data in these documents. I'm not quite sure the difference between connecting documents and connecting data.
Well, you can also click a link and download a file and use it in exactly the same way, and you have your data. But in other cases, the data is available through APIs. So you have a programmatic interface, and you write a little bit of code in a very simple language, and you get your data in this way. It depends on the kinds of data and how they are made available.
Okay.
I'll come with the next question. Is okay, Teresa? Yeah.
Yeah, that's fine.
Okay. So my basically question is this open data. You explained very much. You have this. I mean, the focus is to make this linked, opened European Earth observation data. So that's the aim, to make it more accessible. Can now any person, any SME, use that data? Is it really open source, free to use?
Yes, the Copernicus data is all open and free. But I think in some sense, it's still very much hidden in the sense that you have to go to specific platforms for using this data. For example, you have to go to what we call the DIASes, where DIAS means Data and Information Access Service. So these are platforms. There are actually 5 in Europe, where you can go to them. You find Copernicus data there that you can use to develop an application. The data is free, but if you want to use it in the platform to do some computation, etc., you have to buy computing power from the provider of this platform. But the data is free. Yes, the answer is yes.
Okay, great. That comes directly to the next question. I've then maybe now Teresa, and then I have another one. Teresa, you have one?
Yeah, it's kind of connected to your question before. So would it be possible to, I don't know, create an app or something like that to get the information directly to the people so that we can have the connection and the information about maybe something that would interest us or some, I don't know, natural catastrophes, so that we would know that something would happen. For example, here in Germany, the flood that just happened in North Rhine-Westphalia, one of the many problems was that it caused so much damage that people didn't know, that it wasn't really communicated. So would there be some kind of app or system that you could communicate with us better, and that people would know and can act accordingly?
We have not developed such an app ourselves, although the system that we have for visualization of such information, that would be the closest to what you are asking for, Teresa. This can also run on your tablet or on your mobile phone. So you can see, for example, these nice maps on your mobile phone. So in the case of an emergency, this is what I would think would be the most useful. I mean, be able to have an application, as you say, where people are informed, and then they can browse a map to actually learn more about the current situation. And the map is updated on a real-time basis to keep people informed about the developing situation. So in that case, again, I think semantic technologies are interesting because it is very easy to build such applications, such like the ones that you suggested, using visualization tools like Sextant that I talked about earlier.
Okay, maybe that links to my question. So now we need somehow SMEs or entrepreneurs.
I'm sorry, I have to interrupt you. We can't see you right now.
Okay, then it's again but you hear me, right?
Yeah, we hear you.
So that's enough.
Yes, we can hear you.
The only question is how we get, that's for Manolis, how we can get more students, startups and SMEs involved in studying and using this Earth observation open link data. You have an idea?
Well, I think there is already a very healthy downstream economy in the in Europe. There are a lot of SMEs that are doing this. They are not necessarily using semantic technologies that we preach. Maybe they are using different technologies, but they are working with Copernicus data and satellite data. So I think the availability of open Copernicus data free to everybody, and the fact that there is already some healthy industry out there working with such data will also allow us to to continue and see more developments in this area. I mean, certainly the Union is doing its best to facilitate this with the various activities related to Copernicus. It's not just for academics, but it's also for companies, right?
Yes, yes. It's just like it's somehow it's still, I mean, that's why we're doing this. Okay, this can be open, public, and the recording will be published. It's sometimes still mysterious for people who are not in the research area how to get the data. No? There's still needs to be some public work, some dissemination to the people. Yes, and that comes to my last question. We all think it's not only data is the problem, but it's of course also this. We call it human level artificial trustworthy AI. Is this wonderful paper, which many years now experts meeting on this. So the last question I give, I mean, many think not only data, but also trust is the oil for AI in Europe. Do you have an example of trustworthy AI? It's difficult.
No. I mean, I can give you examples of trustworthy AI in other domains, but not with Earth observation. I suppose the closest that I can imagine is information that that is associated with other information that is also socioeconomic. It is quite possible then that you get a system that produces information that is biased in some way. And you might have a map and the various, let's say in certain areas, you see certain statistics that are biased. But it doesn't have to do with the sensor of the satellite. It has to do with the sensor of the sensors of the people. It has to do with the socioeconomic data that you relate. Like I said, that typically satellite data never go by themselves. They usually have company, and some of that company might be socioeconomic data. That would be the closest thing that comes to my mind at the moment. And for that reason, we need, as you rightly said, trustworthy AI, and this is why Europe is investing so much in this area.
Yes. So I think the questions are asked. Teresa, a question left? The audience has no question.
Yeah, I do have one last question left as well. For me, that would be about more communication and more connection. Is the semantic technologies, are the semantic technologies usable to connect different associations or organizations, I don't know, company like you who do that do Earth observation, if they connect their data and can access the data from other organizations? Is that possible to make the communication between these organizations or associations more efficient and to work together to, I don't know, like Carmen asked as well, to save the world or do more to be able to detect natural catastrophes and, you know, about climate change? Is it possible to work better together because of these semantic technologies?
I suppose the closest thing that comes to my mind now that is related is the concept of data spaces, which is also something very interesting that also the European Commission is putting a lot of emphasis, and work in Europe, let's say by the International Data Spaces Association, also by activities like GAIX, are putting a lot of emphasis in this way. Data spaces do not necessarily need to use semantic technologies, but I think they can be built very, very nicely using semantic technologies. And if we are thinking about data spaces of Earth observation data, for example, then you can bring together all these aspects that you alluded to in your question.
Okay. Thank you. I think I'm checking here also. Everything is said, everything. So, thank you, Manolis. This is really, I'm very inspired by Earth observation. You are, for me, it's incredible treasure, no, out there. And especially for the live Earth observation. It's there's yet so much to do. And so I hope we inspired some people also in the audience. And I will send you the recording, Manolis, afterwards, no, when it's processed. And you tell me if it's okay, and then it will be published on the AI for You video channel if I get from you green light and else not.
Okay.
And thank you. And if anybody has more questions, you can forward it to Manolis, or if you forward it to me, then I forward it to Manolis. So it will be ending up at the speaker. And thank you very much, and have a nice day. And thank you, Teresa. Thank you, Manolis. And thank you, everybody in the cafe. Bye-bye.
Thank you, Carmen. Thank you, Teresa. Bye-bye, everybody.
Bye-bye.
Thank you.